Okay, so the squeeze theorem is kind of pictured right here, this idea. All right? We're trying to find the limit of f of x. If f of x is always between two functions, which you can see in this picture, from what you can see of it, f of x is always between two different functions. It's always less than h of x, but it's always greater than g of x, okay? If it's always between, okay, or equal to, all right? If the limit of h of x and the limit of g of x are both equal to a given number, then wouldn't it be logical then that the limit of f of x also would be that same number?
Yeah.
As long as f of x is always being squeezed or is always between those two functions. That's the whole idea of the squeeze theorem. If you can't find the limit of f of x, but you know f of x is always between two other functions, you would know that if those other two functions have a limit of 7, well then f of x must also have a limit of 7 because f of x is always in between those two functions there. Okay, it's kind of logical, it makes sense, all right, but you need that. It's basically another method of finding the limit of a function when you can't just plug in a 0, okay? So let me find the actual definition here for you. I think we got to go to page 65 to see the true squeeze theorem. I'll write it out here. If h of x is less than or equal to f of x, and that's less than or equal to g of x, so in other words, f is always in the middle of two functions, okay? And I'm shorting this just a little bit here. And the limit as x approaches c of h of x equals some number, but that's the same limit as x approaches c of g of x. So basically the two outermost functions, okay, they equal the same thing. Their limits equal the same thing. Then it would make sense that the limit as x approaches c of f of x would also equal L. Okay? That is your squeeze theorem. You don't need to have that memorized, you just need to have the idea memorized. Okay? Now I'm going to kind of show you how you can use that squeeze theorem with this one right here. Okay? Alright. First of all, I'm going to show you how this function right here, x squared times the sine of 1 of x, that is always going to be between negative x squared and positive x squared. Okay? I'm going to show you that between negative x squared is always going to be less than or equal to this, which is always less than or equal to this. I'm just going to logically talk you through that. Okay? Alright, first of all, when you take x squared times the sine of something, what sort of answer would you always get? Or maybe, if you take the sine of something, what sort of answers do you get when you take the sine of some value? What are your answers always between?
Negative 1 and 1.
Negative 1 and 1. The largest sine value you can ever get, the sine of 90 degrees, the sine of pi over 2, that's 1. Can you ever get an answer greater than 1? No. Okay? The sine of negative 90 degrees at 270. Okay, that would be negative 1. But you can never get an answer that's larger than 1 or smaller than negative 1. So this part of it right here, the sine of 1 over x, that answer will always be somewhere between negative 1 and 1. Well, if this is always between negative 1 and 1, when you take that times x squared, you're always going to get an answer that's either x squared or closer to 0, right? Because if this was 1, if sine of 1 over x, if that does equal 1, well, 1 times x squared is just going to be x squared, right? You couldn't get an answer that's bigger than x squared. If this was negative 1, could you get an answer that's smaller than negative x squared? No. You could get negative x squared. Like if the sine of 1 over x was actually equal to negative 1, you could get negative x squared, but could you ever get anything below negative x squared? No. So does it not make sense then that this function will always be this or bigger, but never bigger than this? So that kind of logical, that makes sense? And everyone you see actually, every one of these limits that you end up seeing, you're going to basically have some sort of trig value in there for the most part, and you're always going to be able to say it's between this and its opposite. Okay, so it's pretty standard, the type of problem that you're going to see with this. Okay, so now because this is always between here and here, all you got to do is find the limit of these two, and then therefore you'll have the limit of this one, assuming these equal the same number, which in this case they will. Okay. So in other words, what is the limit of negative x squared as x approaches 0? 0. Okay. What is the limit as x approaches 0 of positive x squared?
0.
Also 0. Well, because this is always between these, what is the limit then? So basically, therefore, Luke will love this. By the squeeze theorem, and yes, you have to write that, okay? Therefore, by the squeeze theorem, okay, the limit as x approaches 0 of x squared sine of 1 over x will also equal 0. Okay? So that's really the whole idea behind it. There's nothing too fancy with it. Okay? If you can't identify what the limit of some multiplied function is together, because when you plug in 0 you get undefined, okay, well, it'll usually involve a trig function, that's why it's a little bit confusing. But if you can put it between two functions, and then find the limit of those two functions, and if you get the same number, you know the limit of that one in the middle would also have to be the same number because it's always in between those two. Logical, not logical, questions? What's going through your head? Processing, John, I can see it.
Writing stuff down, of course.
It's all in the steel trap.
Yep.
It's all in the steel trap. Shut up.
You have to open that steel trap when you take a test?
Yeah.
That's why it takes so long.
There's a lot of locks on there. Yeah.
Okay.
Lots to sort through because everything makes sense.
I want to show you something on a graphing calculator here in a second too. So when you're done writing this down, go ahead and get your graphing calculators out if you have them. Change it to radian mode. Change it to radian mode.
So cute.
Everybody got this written down?
Yep.
Yep.
Okay. I'm gonna do one that looks a little bit neater than that one does. I mean, we could do it with that one, but that one's not near as fun. I know it's impossible for you to believe. Okay, so let's do y equals x squared sine x. Now I know the limit of this one would have been really easy to find because all you got to do is plug in 0. Actually, you hit the light for me, please, just to help. The limit of this one would be easy because you could just plug in 0 for x to find your limit. But it gives you a little better idea when you see it. So now let's go x squared on the next one. And let's go negative x squared on the third one. Make sure I'm in radian mode. I'm going to hit zoom 6. And I'll try to outline exactly what happened here.
Mine has a whole bunch of bar graphs.
I can't even make one.
Turn your plot off, so go back to y equals,
I can't even make one.
and go up here and highlight plot and hit enter.
I get a graph.
And so then it'll shut it off, now that plot will be
Oh,
gone.
You got this
okay.
building? Well,
There we
I
go.
got it rearranged mine. Oh, you need to.
There's a lot of stuff going on with this.
That's why you gotta have a colored one, it makes it more
I
easy.
know, color would make this a heck of a lot neater.
So right there,
Well, sorry, I don't.
keep the bottom one black and then make the squiggly ones blue. You don't even have, your markers are really just,
Next time you paycheck, go straight to Radio Shack and calculate.
Radio shit.
I'm ready to buy one.
So the red one and the blue one there were your x squared and your negative x squared. Okay? And the crazy one was that x squared sine x. Okay? And what you see is that it's actually always in between the two of them. Okay? Yeah, I mean it's doing this, but if you think about it, that's still in between the red and the blue because the blue ends up going down forever really fast. This other graph is always between them, and in fact right in here it ends up, it crossed right there, and then went back up, and then down, and back up, so it did kind of a weird sine curve. But it's definitely always between the red and the blue, because the red and the blue get bigger, faster, and it kind of just stays right in between where they're located. Alright? So there's kind of one interesting picture to look at as far as the idea of the squeeze theorem. It's going kind of crazy here, but as it got really close to 0, it ended up going right in between, or actually equaled 0, but it did stay in between the red and the blue the entire time. Okay? See if I can give you another decent one to look at here.
make something pretty.
Yeah. Let's maybe do... Let's try x, cosine, parentheses. I'm just picking one out of the book. I'll see if it's a neat one or not.
X cosine parentheses.
Wait, what are you doing?
What is going on?
What are you doing? What? You're pressing stuff.
Give them a break.
X cosine 1 over x. And then I want to do absolute value of x.
You math it, you know.
Math, number.
Of X.
Wait, where do you go to in the number?
Math.
It's an
and then
ADS.
Yeah, no, mine looks different, so.
Math, number one is absolute value.
Do you have to do the negative out front?
Yes.
Oh, duh, because absolute.
Goodness, man.
We've been.
Did you
I
ask
didn't like
that?
this one.
I did ask that.
Whoa, what's going on?
There's some weird stuff going on in this thing. But it looks cool. Kind of.
Aaron, how can you breathe?
Oh, I don't like that first one. That doesn't look that neat. It's almost a line itself. It's a little bit of a curve. What if I change this to sine? Will that affect it?
Let's see.
No. What if I change it to just
Tangent.
x? Trying to find a neat one here.
If you zoom in, it gets pretty crazy. I tell you. Look at that.
Oh, there you go. That was not bad.
That one's kind of cool.
What are you doing here?
See, that's what mine looks like.
When you zoom in.
Mine says
Oh,
air.
that probably doesn't help, does it?
What'd you put as your Y1?
So I had
X.
x sine x on that one.
Ow.
X sine x, and then I had the absolute value ones. And that one's kind of neat how it's just always going up to it, back down to it, back up to it, and it's always staying right in between. Kind of a good picture of the squeeze theorem there. Okay. So, that's really it. I wanted to keep it pretty short and simple as far as the squeeze theorem goes. Only got 2 problems for you to practice. It's numbers 91 and 95 on page 68. Yeah, thank you.